Hi everyone, welcome to Random Thoughts with Alex. I didn't intend to make a video today, but I made a calculation that gave me some really interesting results and I didn't want to wait to give the results to you. So, what did I do? I wanted to check if 3I Atlas could be propelled by outgassing. Or more precisely, I wanted to calculate if the solar heat that 3I Atlas is getting is enough to produce the outgassing to propel 3I Atlas at the acceleration that has recently been measured. And I can break that up in four questions. The first question is how much outgassing is needed to propel 3I Atlas? We can calculate that. Second, how much heat is needed to create that much outgassing? We can calculate that also. How much area is needed to capture that much heat from the sun? It's also something we can calculate. And then when we put this all together, we can calculate how thin does 3I Atlas need to be to have that much area. And that's the calculation I'm going to make now. So to kind of make that a little more clear what we're talking about, let's assume we have the sun. Now let's assume we have an object at a distance of 1 astronomical unit. Now 3I Atlas is further away from the sun, but the acceleration has been translated into the acceleration that you would expect at 1 astronomical unit. So we can use that as a distance in our calculations. So what is the assumptions that we're making? We're assuming a certain amount of heat is going into the object from the sun. And then next, we're making the assumption that all that heat is used to sublimate material off of that object, and that's going out in the form of a gas, so it speeds out at molecular speeds, and that momentum creates a momentum in the opposite direction of the object, which is the acceleration. And if we put everything together, we can calculate how thick that object can be or should be. And we will try to come up with the largest possible thickness. So now that we know what we're doing, let's add some equations to that. So let's assume that the object has a thickness h and an area facing the sun a. So I'm kind of assuming a flat object here. We'll see soon why I'm doing that. The mass of the object is simply the density times the volume, which is the density times the area facing the sun times the thickness of the object. Okay, the acceleration due to propulsion equals the mass flow of the propellant times the velocity of the propellant divided by the mass of the object. That's an equation that Avilope also uses in his calculations. The heat that is added to the object is simply the heat flux in kilowatts per meter squared times the area of the object, and that heat is then used to sublimate material. So the sublimated amount of material going out is the heat going in divided by the heat of sublimation. So the heat going in is kilowatts or kilojoule per second, and the heat of sublimation is kilojoule per kilogram. And if we divide kilojoule per second by kilojoule per kilogram, we get kilogram per second. And that's it. 4 simple equations that we need to combine to calculate h. So let's do a little more math. Let's take those 4 equations and let's fill in all the data that we have. We know that this object is mainly made of dry ice, so let's use the density of dry ice, 1,560 kilograms per cubic meter. We know from the NASA calculations that the acceleration of the object corrected to a distance of 1 astronomical unit is 1.16 times 10 to the minus 6 astronomical units per day squared. If we convert that to meter per second square, we get 2.33 times 10 to the minus 5 meter per second square, One astronomical unit is 150 billion meters, 150 million kilometers, but 150 billion meters. A day is 86,400 seconds, so we need to square that and put it in the denominator, and we can easily calculate that number. The outgassing velocity should be on the order of 300 meters per second. That would be the velocity of CO2 gas at a temperature of about, well, let's say minus 100 degrees. The temperature, let's say minus 80, minus 90 degrees Celsius, maybe, I don't know exactly in Fahrenheit, probably something like minus 130, 140 degrees Fahrenheit. But that's the temperature of sublimating dry ice. And so we can calculate the velocity of CO2 at that temperature, that is on the order of 300 meters per second. The heat flux produced by the sun at 1 astronomical unit is 1.36 kilowatt per meter squared, and the heat of sublimation of dry ice is 571 kilojoule per kilogram. These are all data that you can easily look up. So from that we want to calculate H. How do we do that? It's actually quite simple. We take the equation for heat and we substitute that in the equation for the mass flux, which is heat over heat of sublimation. Remember, heat is heat flux times area. So when we substitute Q of the first equation to the second equation, we get that the mass flux is, the mass ejection is heat flux times area divided by heat of sublimation. Now the acceleration is that mass ejection times the velocity divided by the mass of the object. So now we have that the acceleration is heat flux times area times velocity of the outgassing divided by heat of sublimation and divided by the mass of the object. And the mass of the object is the density times the area times the thickness. So we find that the acceleration is heat flux times area times outgassing velocity divided by heat of sublimation divided by density divided by area and divided by thickness. We see that area is in the numerator and the denominator, so we can cancel that out and we get whatever remains. Now we just switch A and H in this equation, so we find that the thickness of the object must be the heat flux times the velocity of outgassing divided by the heat of sublimation divided by the density and divided by the acceleration of the object. It's really that simple. We can talk about the underlying assumptions in a moment, but this gives us pretty accurate view of what's happening. So let's just fill in the numbers that we already have determined, and we fill them into the equation, and we find that the thickness is 20 meters, not kilometers, 20 meters. It has been estimated that this object is at least 5 kilometers in size. In other words, outgassing is essentially impossible. It cannot explain the acceleration of 3I Atlas. So let's see, what do we need to do to make this thicker? Is there any way we might have made a mistake and that actually the object is thicker than 20 meters? Well, let's take a look. To make the thickness larger, we could increase the heat flux, but that's impossible. There's only so much heat coming from the sun, and some of the heat is actually reflected back, so the heat flux that is actually received by the object should be less, not more. The velocity of outgassing, well, yeah, it is possible that it's larger. There's a couple of reasons why this could be the case. If for some reason the temperature is higher than the temperature of dry ice, then the molecules move faster. Not all the molecules are CO2, some of the molecules are water. Water is lighter, so it moves faster. But there's not a lot of water in this object, so let's just make this 500 meters per second instead of 300 meters per second. The thickness can also be larger if the factors in the denominator are smaller. So the heat of sublimation, it is what it is. We cannot change that. The density, well, it's not pure dry ice. Maybe there's parts that are empty space. Maybe there's other maybe there's water ice in there that's much lighter, so let's take 1000 instead of 1500. And then the acceleration, it is what it is. We know that with very high accuracy now, so we can't really change that. So when we change the numbers, we can make it as large as 50 meters, which is still a factor 100 smaller than we expected from the calculations of Avi Loeb. Again, we find that unless this object is some kind of a pancake, it cannot actually explain the acceleration, the non-gravitational acceleration that has been observed by outgassing. So, my conclusion, if 3I Atlas is accelerating due to outgassing due to solar heat, then it is at least 100 times flatter than its estimated size. Now that is something that the world needs to know, and scientists need to figure out how this is possible. I am not an astronomer, but I do know a lot about thermodynamics, so I know that these calculations that I've made are accurate. So now it's up to the astronomers to figure out what's really happening with this object. I hope you like this video. If you do, please like and subscribe, and I will see you in the next video.